This is a short introduction to our paper, AffordDP, Generalizable Diffusion Policy with Transferable Affordance. Diffusion-based policies have shown impressive performance in robotic manipulation tasks. However, they struggle with out-of-domain distributions. Though some efforts attempted to enhance generalization by improving the visual feature encoding for diffusion policy, their generalization capability is limited to the same category with similar appearance. We argue that affordance, serving as the manipulation prior, is crucial for generalization to unseen object instances and categories. In this paper, we introduce AffordDP, diffusion policy with transferable affordance, designed for generalizable manipulation to unseen instances and categories. Our key contributions can be summarized as follows. We propose the first framework that combines transferable affordance with diffusion policy to enable zero-shot generalization to unseen instances and categories. Since affordance contains rich manipulation prior that define where and how an agent interacts with an object, it can substantially enhance generalization to entirely unseen scenarios. We also propose a pipeline to zero-shot transfer affordance by estimating a 6D transformation matrix using foundation vision models and point cloud registration techniques. We further integrate adaptive affordance loss guidance that directs the generated action to gradually move towards the desired manipulation in the sampling process. The main pipeline of our method is illustrated as follows. Given RGB input image, we first segment the target object and retrieve the most similar source object from the affordance memory. Then we perform affordance transfer to simultaneously transfer static and dynamic affordance to the target object, which contains where and how information respectively. However, solely integrating transferable affordance as the diffusion condition is insufficient, as it is only utilized during the diffusion training process and excluded from the diffusion sampling process. To address this, we introduce an affordance-guided sampling process for diffusion policy. The affordance guidance is defined as the distance between the robot's end effector position and the static affordance. This guidance during the diffusion sampling process can effectively steer the diffusion output distribution toward target point. Next, we show generalization to unseen objects of our method. By training on these 4 objects for the pick and place task, our method can successfully generalize to unseen instance with distinct appearance and shape. Here we show generalization to unseen categories of our method. By training on these 4 objects for the open door task, our method can successfully generalize to the unseen category, car refrigerator. Furthermore, we show generalization to unseen scenes. Trained on a single scene, our framework achieves zero-shot adaptation to unseen environments, for example, a kitchen environment. Last, we provide more qualitative results in our simulation experiments. Thank you for watching. For more details about our method AffordDP, please refer to our paper.